Hi, welcome to Math 389 Advanced Analysis. And so what I want to do today is we will start the random matrix theory. So I will leave the double sixes generalized as a fun problem for people to think about. My freshman year in college, Frank Firk, my physics professor, gave us an interesting problem to think about so we would have something to talk to our family members over the Thanksgiving table. He was a little optimistic over who we would be meeting at the Thanksgiving table, but I will leave you with this. So remember, he is a good physicist. A good physicist knows how to manipulate things, okay? So the problem is, and then we'll go to random matrix theory when I'm easier. Solve the integral of f equals f minus 1, where we define the integral of f to be the integral from 0 to x of f of t dt. Okay, so I want to find a function that when I integrate, I get back the function minus 1. Anybody have any thoughts about what might work? Can you think of any function where when you integrate it, you get the function back? E to the x. So let's guess f of x is e to the x. Then the integral of f is the integral from 0 to x of e to the t dt. Well, that's e to the t at 0 and x. That's e to the x minus 1. Yes, that is f of x minus 1. So that works. Now you've seen this in complex. I think we did this in complex. Okay? But this fits nicely into this class. So let's try to solve. So we want to solve the integral of f equals f minus 1. So this is the same as f minus the integral of f equals 1. Yeah. Or 1 minus integral acting on f equals 1. So f is 1 minus integral inverse acting on 1. Which of course is just 1 plus integral plus integral integral plus integral integral integral. I told you, he's a good physicist. Okay? Now, what is the integral of 1? That's the integral from 0 to x of 1 dt. What does that equal? X. Now, the integral of 1 is the integral of the integral of 1. Well, the integral of 1 is the function x. So I now integrate from 0 to x the function, t dt. What do I get? And please say it properly. I get x squared. Nope. Over 2 factorial. And this is really x over 1 factorial. Integral of 1 is the integral of the integral of 1, which is the integral from 0 to x of t squared over 2 factorial dt, which becomes x cubed over 3 factorial. Therefore, f of x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. So this is a class about order of operations. Am I allowed to replace 1 minus integral with the following expansion? So is this legal? 1 minus integral inverse is 1 plus integral plus integral integral plus integral 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 plus dot dot dot. If yes, under what conditions?
You're a physicist.
So if you're a physicist, and it wouldn't be what conditions, it would be what conditions? You'd punctuate it differently.
The integrals are, or at least acting on certain elements, the integrals are absolutely.
So what would you need? The integrals are acting on this. So you need integral takes a space of functions to another space of functions. And what should be true? Well, so interestingly, I just used something like this in probability earlier today. What formula are we really using? To do the expansion, what formula are we using? Geometric. And so whenever you're using any formula in mathematics, what's the first thing you should always ask? So using geometric series formula, what should we ask? Yeah.
Wait, I thought this is the inverse of the verse.
Well, 1 minus integral inverse is 1 over 1 minus integral is 1 plus integral plus integral integral plus integral 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 plus dot dot dot. Right? I mean that's what we're using for the inverse.
Well, I guess one way to make sense of it is to multiply the
Well, but what I'm saying is, what are we, if we're using the geometric series formula, what are we assuming?
oh, like the integral is less.
What are we assuming?
Somewhere.
What is less than 1?
Value
R is less than 1. And R is... No, not 1 minus integral. So it looks like R is integral. So maybe need to restrict to space where the norm is less than 1. Now, if I give you, say, 1 minus a, and I'm sorry, I'm thinking matrices, which is why I wrote I. So I'll do it this way. I give you 1 minus a, and I give you 1 plus a squared plus a cubed plus dot dot dot. And if you expand, well, when the 1 hits everything, oops. When the 1 hits everything, let's put them in different colors. So I'll put the 1 in gold, and I'll put the A in green. So when I do things with the gold, I will get 1 plus a squared plus a cubed plus dot dot dot. And when I do things with the green, I'll get minus a squared minus a cubed minus dot dot dot. And what does all of this simplify to? 1. So in some sense, if I have an operator, the inverse of 1 minus a is 1 plus a squared plus dot 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 if the operator norm is less than 1. So this looks like this might be a way to justify. So again, if you're looking for something fun to write up on the advanced side, make this rigorous. We need to figure out what is the space of functions that we're working on. Will the integral define a map from a space of functions to a space of functions? How would we define the norm on that space of functions? Will the norm be less than 1?
Wait, but in the example, I don't think the norm is 1. Or I don't even think the norm is less than 1. So
if the norm is not less than 1, it's still possible we might get the right answer.
Yeah, but...
And so you have to be very careful that there's a difference between a necessary condition and a sufficient condition. Can you give me a sufficient condition to win a game? Any game.
Have 21 in blackjack.
Have 21 in blackjack, but could the dealer have 21? Usually, I think if you have 21, I think that overrides if the dealer has 21.
Depends how you play it.
So that's a sufficient way to win in blackjack. Is that a necessary way to win? No. And so there could be other ways. So it might be the case that if the norm is less than 1, this can be justified. But it might also work even in the case when the norm is not less than 1. Right, so now that we're at full strength, we will go to random matrix theory. So the professor I was mentioning, Professor Firk of Yale, was a nuclear physicist. And he was one of the original experimenters who was gathering data on the energy levels of heavy nuclei, which led to the subject of random matrix theory, trying to model heavy nuclei. And how much physics do people know? Does everybody know at least gravity? All right. So if I give you 1 point mass in the universe, does everybody agree that that's not too difficult under gravity? If I give you 2 point masses in the universe under gravity, does everyone agree it's not that difficult? So by induction, if I give you 3 point mass, now all of a sudden, as soon as you have 3 point masses, we can no longer write down a closed form expression for what happens. Imagine how much worse it is with something like heavy nuclei such as uranium. We have over 200 protons and neutrons. And so Wigner's great insight was to basically say, rather than trying to solve the actual problem of uranium, let's use the ideas from statistical mechanics. So quantum mechanics can basically be reduced to the following. H of Cn is En Cn, where this is the energy state or the energy level, and this is the energy eigenfunction, and this is the Hamiltonian. So quantum mechanics is concerned with solving problems like this. So you can view H as a matrix, and we're trying to find the eigenvalues, which are the energy levels, and then the eigenvectors have importance as well. But we really care more about the eigenvalues. Everyone here should have done linear algebra at some point. This is a linear algebra problem, but there's 2 reasons why you will never see this in an introduction to linear algebra problem. So there's some issues. The first is H is infinite by infinite. And I assume for the most part, when you do linear algebra, you do not deal with infinite matrices. And the second is we don't know the entries of H. So I want to diagonalize an infinite by infinite matrix where I don't know of the entries. Good luck. Not happening. I have more of a chance, I think, of making this argument rigorous. Okay? So Wigner's great insight was basically to say, screw that. Look at random n by n matrices. For a very large n by n matrix, calculate the physics. And then choose another n by n matrix and another and another and another and average over. And the hope is that a typical matrix will be close to the system average. This room has some interesting geometries depending on who's teaching, in terms of which way everybody is facing. Okay. Anybody know roughly how many air molecules are in this room? To within, say, 6 orders of magnitude.
What's the radius?
I'm sorry?
What's the radius?
How many liters of air do you think are in
So who remembers their chemistry? Well,
here? Like, I know 22.4 liters of air is a mole. Wow.
okay, good. So how many molecules are there in a mole?
6 times 10 to the 20.
Yes. So do you think there's at least a mole here?
Oh, for sure.
Do you think there's at least 10 moles?
Yes.
Yes. Do you think there's at least 100 moles? Remember, you only have to be within 6 orders of magnitude, right? Do we all agree that there's at least 10 moles in here? Do you think there's more than 10 to the 12 moles?
No.
No. So if I guess like 10 to the 6, 10 to the 7, I would be fine. So if I guess that many moles, that would be like on the order of like 10 to the 30th atoms in the room. I should be fine. So within 6 orders of magnitude, 10 to the 30 atoms in this room. Is it possible that all the air molecules are in the front half of the room? Theoretically, yes. And those of you in the back of the room, it could be your unlucky day. This is why I don't have all the students sit in the same part of the classroom. At least some survive. The death rate in my class has never exceeded 10% in all of my time at Williams. And I won't say how close we've come to 10%, but it's always been. So is anybody, and again, I want you to feel safe and comfortable. This is supposed to be a nurturing environment. Is anybody worried about suffocating? Why not? So let's say there's, if 10 to the 30 atoms, let's just say all that matters is the atom is in the front or the back. Let's say 2 times 10 to the 30. Well, actually, it's probably better. It's probably better for the next calculation, 10 to the 30. How many atoms do you expect in each half? 1/2. And what do you expect the fluctuations to be on the order of? Around 10 to the 15th, right? And then you can start to play all those games. It's 1/2 times 1 minus 1/2. Take the square root of that. But so something on the order of 10 to the 15. So if we divide by 10 to the 30 to see what fraction of the molecules are in each half of the room, each has essentially half. And the fluctuations are so small, we're not worried about it. So Wigner's great insight was to basically reduce quantum mechanics to statistical mechanics and say, rather than trying to write down the Hamiltonian for this particular system, let me just consider all matrices, put a probability distribution on them, calculate what's going on for n by n matrices drawn from this distribution, and then take the limit as n goes to infinity. So again, we have some kind of limit process. So we're going to have to worry about how do we scale things. And we can figure that out. And the hope is that a typical element will behave like the system average. Do you think this is a reasonable assumption? So if I choose, we have, say, 2,200 students at Williams, roughly. If I choose a student at random, do you think all of you are going to be, that anybody I choose is going to be close to the system average? So I can just pull out any random student, and they'll be close to the system average.
What's the system's average?
What is close?
So one question is, what is close? And then there's something else you should be asking. What do you mean? What do you mean by what is the average?
You said like an average Williams, but average by what's that?
Right, but what statistic are we looking at? So for instance, I will risk saying this politically. Let's say we're looking at, I'll do it biologically. I'll do it chromosomally. Let's look to see what is your, are you XX, XY, XXY, XYY? What do you think? Is there a good system average for something like that? No. Now, if you look, roughly half are going to be XX and roughly half are going to be XY, and probably vanishingly small for the other stuff. But an individual person can't be close to that because it's discrete. So for certain categories, there's no way you can be close to the system average. Another way of looking at it is every Williams student has either a $10 bill or a $20 bill on them that was given to them by the trustees as just, thank you for attending Williams, and signed personally by Maud. Okay. If I look at the average amount of money that people have from the trustees, what do you think it would be? If I choose randomly what you get, 15. And is anybody going to be close to 15? Not really. half of you will be around 10 and half of you will be around 20. So there are certain quantities that will not be where, a random element has no chance of being close to the system average. So for a lot of the things you're looking at, it's not enough to control the averages. I need to control standard deviations as well. For other things, they might do really good, like SAT scores. Probably if I choose a student at random, that should be fairly close to the average scores. So it really depends on what statistic you want to look at. Should I assume people know linear algebra, or should I just say, wouldn't it be nice to be leisurely and review linear algebra? Assume? Okay, so can people prove that the eigenvalues of a real symmetric matrix are real? So right now, your grade depends on this. Pop quiz. So A is real symmetric. Eigenvalues of A are real. Go. How do I do this?
Sandwich the matrix between eigenvectors.
Okay, so I know A equals A transpose and assume AV equals lambda V. Now what do you want me to look at?
V transpose A.
Good. And we can view this two different ways. V transpose A times V, or V transpose times AV. But this is the same, so I dropped the transpose. This is the same as V transpose A transpose V, because A equals A transpose. But V transpose A transpose is what? AV transpose V. And now AV is just going to be lambda V transpose V equals, keep dropping the transposes, is V transpose lambda V. Well, I can pull out the lambda, and this is just V transpose V equals lambda V transpose V.
Lambda is complex, and you would have to do the complex.
So right now, this gave us nothing, right? Okay, so let's fix it. So this is the advantage. So rather than looking at V transpose V,
I'd be clear to just write it in the
so I can just change things ever so slightly. And what I'm going to do now is I'm going to do the Hermitian. And so A Hermitian is A transpose complex conjugate, or the transpose and then take the complex conjugate. So the Hermitian is the complex conjugate transpose. And so the calculation is going to be very, very similar. So now, as I start putting in the Hermitian, this is the same as V Hermitian, A Hermitian, because if A equals A transpose, then A equals A Hermitian if A is real symmetric. So under the additional assumption that A is real, not just that A is symmetric, that A is real symmetric, then this is the case. And now the Hermitian, the complex conjugate transpose of the product is just the product of the complex conjugate transposes in reverse order. And now when I take the complex conjugate transpose of lambda times V, I will get the complex conjugate transpose of V, and I'll get the complex conjugate of lambda. And on the other side, I just have the complex conjugate transpose of V going throughout. And so I'm left with the absolute, the complex conjugate of lambda times the length of V squared equals lambda times the length of V squared. Thus, lambda equals lambda bar, which means it has to be real. So what went wrong with this earlier argument?
Did anything go wrong? I think it just that doesn't really give you any result. Like,
So it doesn't give us any result.
but it didn't go wrong.
So this becomes a linguistic question as to, do we consider that something went wrong or just nothing went right? And so, you could put a positive spin on it and say nothing went wrong. It's just at the end of the day, it just wasn't useful.
Maybe we should have started with the assumption that we want to reduce it to something that will tell us that the imaginary part is 0.
Mhm.
And for that, we should have done something related to conjugates, one way or another.
And so here just, the transpose of lambda, it's just a number. It's just going to be lambda. It doesn't change anything. Whereas as soon as we're using the Hermitian, we now get the complex, so it changes it. And this is going to allow us to explore some properties of lambda that we wouldn't get otherwise. Is it possible for V transpose V to be 0 without V being 0? Just a side note, lambda is an R if A equals AH. And these are called Hermitian matrices. So this is the complex generalization of real symmetric. If you equal your complex conjugate transpose. So can V transpose V equals 0? All right, so everybody agree V transpose V can't be 0?
It's the norm, right? It's the normal. The norm V equals 0. You can't do the factor itself.
So okay, so is it a norm? Is V transpose V a norm? It depends on whether or not V is in C or in R. Right? I didn't write anything here. This is the nice thing about recording the lectures. I can go back. I never said anything was real. So if I start off with, AX minus, or let's say plus B equals 0. So if the coefficients are in N, are the roots in N? No. Roots are in what? Q, not necessarily in N. And as an example, if I take 2x plus 1 equals 0, that gives me the root of 1/2. So what this means is if I look at linear polynomials with integer coefficients, the roots do not have to be integers. What if I look at integer polynomials? I'm sorry, what if I look at linear polynomials with rational coefficients, will the roots be rational? So linear polynomials with rational coefficients. So linear with integer coefficients, roots not necessarily integers, but if rational coefficients, roots are rational. So what this means is that the rationals, the linear polynomials with rational coefficients, we don't have to expand our space beyond the rationals to get the roots. What if I start looking at quadratic, ax squared plus bx plus c, coefficients in n? What are the roots in? But do I have to go as far as c? I need all of c, anything in c can occur. Yeah, so the roots are in, well, q joined I is not enough.
Yeah, like square root 2.
Right?
Yeah.
Roots are in, well, but
sorry.
Right. So I don't need all of R.
Like all the square roots. And
All the
also
algebraic.
Q join all the square
So I know the roots are going to be in negative what? So roots are negative b over 2 plus or minus the square root of b squared minus 4ac, oh sorry, over 2a, all over 2a. So if I keep a, b, and c to be integers or rationals, then the real part is going to be looking like an integer or a rational. Except for what if b squared minus 4ac, that could be positive square root. So I could get real numbers to be of the form rational plus rational times the square root. I could also get an imaginary part that is going to be an imaginary number times the square root. Could I get, if a, b, and c are rational, can I get, say, 3/2 square root of 7 plus the square root of 11i? Is that possible? No. If the real if b squared minus 4ac is greater than 0, there's no imaginary part. If it's less than 0, that's the only place I can get a square root. So I can't have something like this. So there's going to be no quadratic with rational coefficients that will have this as a root. I can find a polynomial that will have this as its root, but it's not going to be a quadratic. So one of the big questions you always ask is, where do things live? And this is, to some extent related to what we started today with. Where does this operator live? When can we expand? What is amazing is once you add the root of x squared plus 1 equals 0 to R, any polynomial of degree n with coefficients in C has all of its roots in C and n of them. And that includes multiplicity. So this is amazing that once we add in the solution to x squared plus 1 equals 0, we don't need to add anything else to solve cubics or quartics or quintics. That's it. So could B transpose B be 0? So can you give me a vector V such that V transpose V equals 0? I1 or 1I. So let's do 1I, 1I. There's going to be 1 squared plus I squared is 0. So it is possible, and this is why we take the complex conjugate. Can you give me a matrix where that might be the eigenvalue? I mean, the eigenvector. Or can anybody,
0 minus I.
0 minus I 0? Well, this, okay, so this is really the same as I times 0 minus 1, 1, 0. Right? So let's just study 0 minus 1, 1, 0, because that extra I that you have is really not changing anything about the eigenvalues, right? So you've chosen a really good matrix. What does this matrix do? I might have chosen a slightly different matrix, but does anybody recognize this matrix? It does. And this is where I hate being the professor, because I'm now on the spot. For the rotation matrix, it's cosine theta, sine theta, sine theta, cosine theta, right? But one of the signs has a minus sign. I normally do the upper right. And let's look at what happens if you do, say, r of theta of 1, 0. Then that's going to go to cosine theta, sine theta. And r theta of 0, 1 is going to go to minus, I'm sorry, we have 0, 1, so it's going to be minus sine theta, cosine theta. So let's think about what's going on. Here is the coordinate axes. Here's the vector 1, 0. And now it moves to cosine theta, sine theta. So we've moved this theta radians. The other one is 0, 1. And now we move it to minus sine theta, cosine theta. And then that should also be moving it theta like that. So it's going to have a positive, theta is a small number, it's going to have a positive y component and a negative x component. This is essentially the same as just churning by theta radians. So if you look at 0 minus 1, 1, 0, if I wanted to write this as r of theta, what would theta equal? Pi over 2. So let's think about it. I want an eigenvector. Okay? I apply a rotation matrix. I rotate the vector by 90 degrees, and I want it to be pointing in the same direction. Are there any vectors you know of that when you rotate them by non-zero vectors, that when you rotate them by 90 degrees, they're pointing in the same direction? Other than zero vectors? No, right? Well, let's just, for kicks and giggles, I think that's the expression, let's look at what happens if we apply the vector 1i. Then we would get negative I and 1. I can pull out a negative I, correct? And then I would be left with 1. And if I pull out a negative I from 1, what do I get? I. It's an eigenvalue. So we've just shown that this is an eigenvalue, minus I, and 1i is an eigenvector. So you've actually just found a way to look at this where I have an eigenvector. I've got to do things in the complex plane, which I find problematic. And now it's not so surprising that I've got V transpose V equals 0 because V doesn't have real coefficients. I'm sorry, V doesn't have yeah, V doesn't have real coefficients. It has more than just real coefficients. And if I want to calculate its length, I really need the complex conjugate transpose. If I do V complex conjugate transpose V, that's going to be 1 minus I with 1 and I. And now that's going to be 1 plus 1, which is 2. And that makes sense. This vector should have length square root of 2. So everything works out. Okay. So the next is we need to know a little bit about orthogonal and unitary matrices. So what's the definition of orthogonal?
Well, the transpose of the matrix is the inverse.
Good. So Q inverse equals Q transpose. And I think we want maybe Q to be real. So Q transpose is Q transpose Q is the identity. And unitary is Q, use U. U inverse is U Hermitian. So U Hermitian is U Hermitian U is the identity. What can you tell me about eigenvalues of orthogonal and unitary matrices of size 1? And for the orthogonal matrices, because they have real entries, are they just plus and minus 1? So do orthogonal matrices have the absolute value of their eigenvalue equal 1 as unitary matrices have the absolute value of their eigenvalue equal 1. So what do you think? We will prove shortly that unitary matrices have eigenvalues of absolute value 1 and only that. Orthogonal matrices are special unitary matrices. They have real entries and, Q inverse is Q transpose. The only real numbers of absolute value 1 are plus and minus 1. Therefore, orthogonal. Do people agree with this? Why not? Yeah, we just saw. Note 0 minus 1, 1, 0 is R of theta. And R inverse of this is this is a specific theta. This is pi a halves. And R inverse of pi halves is actually just R of pi halves transpose. And it turns out it's also the same as R of minus pi halves. So this is orthogonal, but has complex eigenvalues. So this is extremely important. You can't just say orthogonal is like unitary, where now you restrict the results to being real. So the proofs are actually not too bad. So theorem U unitary implies the eigenvalues of U have 1 in absolute value. And the proof is, let's look at V Hermitian, U Hermitian, U Hermitian, V, where UV equals lambda V. Why would I look at something like this? Yeah, this is just the identity. That's why I'm looking at this. I'm really starting off with, the identity equals, oops, I have too many Hermitians, sorry. I just start off with the identity is U Hermitian U, and now let's just sandwich that with an eigenvector. That's where I'm looking at this. And now what I can do is I can group things together. And on this side, this is just V Hermitian V. And on this side, this is the same as UV, take the Hermitian of that with UV. And so this is just the length of V squared. And now I'm going to get lambda V Hermitian, lambda V. And now when I take the Hermitian, I'm going to get the complex conjugate transpose of lambda. And then I'm going to have lambda from the other one, and I'll have V Hermitian V. So I get the absolute value of lambda squared times the length of V squared. So the absolute value of lambda squared equals 1. Therefore, the absolute value of lambda equals 1. And so this is the proof that unitary matrices have eigenvalues of 1. Can I do this proof for orthogonal matrices? Can I replace U with Q? If I keep the Hermitian, can I replace U with Q? Yes. So, proof works with Q instead of U with Q a real orthogonal matrix. So the absolute value of eigenvalues equals 1 if Q is real orthogonal. Because a real orthogonal matrix is also a unitary matrix. Can I do this argument with transposes rather than Hermitians? What breaks down? Not do with transpose and real orthogonal in place of Hermitian and complex and unitary. Sorry. What goes wrong? Why can't I just replace U with Q, H with T? I mean, if I did that, I would get, V transpose V is lambda, I'm sorry, I would get is lambda squared. V transpose V.
Then V transpose V could be 0 or non-zero.
Right, so this could be 0. We can't deduce anything about lambda because V transpose V could be 0. If V transpose V is not 0, can we deduce anything about lambda?
Yeah, like 1.
It's length 1. Can we deduce more than that?
Oh. Lambda's
Well, so do we know lambda is real if V transpose V is not 0? Yes, right? If V transpose V is not 0, I can cancel it from both sides and I get lambda squared equals 1. What are the only things where lambda squared equals 1? So if V transpose V is not 0, then lambda equals 1 or minus 1. So yes, that would be true. But in general, we don't know that V transpose V is non-zero. So we know that the eigenvalues of real symmetric matrices are real. We know the eigenvalues of complex Hermitian matrices are real. We know the eigenvalues of unitary matrices have absolute value 1. We know the eigenvalues of orthogonal matrices have complex value 1. The last result we really need to know is that you can diagonalize a matrix. Does everybody know how to prove that you can diagonalize a matrix? Are people comfortable that they can prove it right now? You know, it's right before spring break. I'm getting tired. Can someone come up here and prove right now?
It's like a deduction.
You can do it by induction. So my freshman math professor said, when somebody asked him, when is something obvious that we don't have to write all the details? He said, and you probably cannot do this in 21st century America. If I can come to your dorm room at 2 or 3 in the morning, wake you up, have you solve the problem immediately, and you can go back to sleep and sleep soundly, it's obvious. Other than that, I want to prove. So can you prove that you can diagonalize any real symmetric matrix? So, the big questions are diagonalization. So if A is n by n with n distinct eigenvalues, it's diagonalizable. And so what we can do is we can say, let's let A of Vk equal lambda k Vk. K goes 1, 2, all the way up to n. And let's let S be the matrix V1 as the first column, all the way to Vn as the nth column. And I always forget which way do you want to make the matrix Sn versus Sn of S. So if I take lambda to be the matrix lambda 1, lambda 2 to be a diagonal matrix, it's easy to find the eigenvalues of this matrix. Right? What are the eigenvalues of this matrix? Lambda 1, lambda 2. Okay, this much linear algebra we all remember. Great. Can you find the eigenvectors? Yes, 1, 2, 3. So now, if you look at what happens, S takes EK and gives you VK, and S inverse takes VK and gives you EK. Are we happy with this? Are you sure that S is invertible? How do you know S is invertible?
Well, because you have distinct eigenvalues, so the eigenvectors are or linear.
So how do you know the eigenvalues are linearly independent?
You can prove it. It's the eigenvalues are distinct.
Okay, and how would you prove it?
Basically, you write.
So we'll pause this for now. So assume S is invertible. It's not bad every now and then to just revisit some earlier classes and just see how would we prove this. So now we know S of EK is VK. And we know A takes VK to VK, right? So if I looked at AS of EK, what does that equal? It equals lambda K VK. So if I look at S inverse AS EK, that's going to be S inverse of lambda K VK. That's just lambda K S inverse of VK, that's just EK. So S inverse AS acting on EK gives me lambda K EK. Oh, that gives us the kth column of this matrix. So S inverse of AS is just the matrix lambda. So if we have n distinct eigenvalues, we can diagonalize, assuming that the matrix S is invertible. So we now need to prove S is invertible. So lemma, A has n distinct eigenvalues S as before, then S inverse exists. And so we have, S is V1 dot 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 Vn. So,
That's how you can prove that if like an n by n matrix has its column vectors independent from have their column vectors independent from each other, then it's basically
good. So the only reason the only way it would not be invertible is if S has to send some vector to 0. So if not invertible, there exists a vector, let's say, B1 through Bn, such that S of B equals 0, or B1 V1 plus dot 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 Bn Vn equals 0. So is it possible that the V's are not linearly independent? So I agree with you that if we can show the V's are linearly independent, then it's invertible. Because the only way that that could then be 0 is if all the V's are 0. So to show S inverse exists, you show, enough to show V1 through Vn are linearly independent.
and you can say like an arbitrary linear
Good. Okay, so assume not. So assume, let's say, B1 V1 plus dot 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 plus Bn Vn equals 0.
And then you can apply A.
Good, apply A, and then we'll get lambda 1 B1 V1 plus dot 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 plus lambda n Bn Vn equals 0. Okay. Now
wait,
what?
no. I think we're supposed to apply like A minus, let's say, lambda. Okay, let's just say that.
Well, I could always multiply the first equation by something.
Yeah, I think we can apply like something like A minus lambda I. Lambda 1 I.
Well, what could I multiply the first row by? Lambda 1 or,
Just any lambda.
right, so instead of doing lambda 1, what might be a nicer one to do? I think there's a better one to do than lambda 1.
Lambda.
Which lambda? Lambda n. Then you'd get, lambda n b1 v1 plus dot 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 plus lambda n bn vn. And now when you subtract, you would get lambda n minus lambda 1 b1 v1 plus dot 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 plus lambda n minus lambda n minus 1 bn minus 1 bn minus 1 equals 0. Is that a contradiction?
I think gonna keep applying this.
So you keep applying this. What you can do is if the eigenvectors v1 through vn are not linearly independent, choose the first subset of them that is linearly dependent and no smaller subset is linearly dependent. And then this would have given you something better. So instead of going all the way up to n, we should go up to some m. So we fix this by saying, if linearly independent, let m be smallest integer so that v1 to vm minus 1 are linearly independent, but v1 dot 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 vm are linearly dependent. And now all I have to do is change these n's to m's. And now I've just found a smaller set of vectors that are linearly dependent. Therefore, my assumption is false, and they are linearly independent. And so if your matrix has n distinct eigenvalues, then you are diagonalizable. Everybody comfortable with this now? Is every matrix diagonalizable? So give me a matrix where you have, so okay, so if your matrix is not diagonalizable, what must be true? You don't have n distinct eigenvalues. Is every matrix where you don't have n distinct eigenvalues not invertible, not diagonalizable? So we just showed that if you have n distinct eigenvalues, you can be diagonalized. So I will, don't share this with one of my colleagues. So if n distinct eigenvalues, then diagonalizable. If you don't have n distinct eigenvalues, are you not diagonalizable?
Oh, just any diagonal
Yeah,
values.
just take A equal, d1 through dn. So you've got to be very careful about negating things. If you win the Super Bowl, then you very tautological. Let's do something a little bit less tautological. If you won the Super Bowl, then you
Or a football player.
are a football team.
Yeah.
Does that mean that if you're a football team, then you win the Super Bowl? Yeah. If you win the Super Bowl, then you played in the Super Bowl. If you played in the Super Bowl, does that mean you win? No. And this is where one of my colleagues have to be careful because her team played in the Super Bowl 4 straight years and did not win any of them. What if I say, if you won the Super Bowl, then you scored more points than your opponent? That's equivalent. Then yes. Then if you score more points than your opponent,
There's not like some weird disqualification.
yeah. If you've seen dodgeball, congratulations for your victory and disqualification. So this is the difference between necessary and sufficient. So if you have n distinct eigenvalues, then you're diagonalizable. But this is not the only way that you're diagonalizable. We do know, however, that the only matrices that are not diagonalizable are those that do not have distinct eigenvalues. And so everybody should know the example of at least one non-diagonalizable matrix. Anybody know example? So 0, 0, that's diagonalizable. Anything works.
Yeah.
I'm sorry?
1, 1, 1. I don't know.
Well,
1, 0.
1, 0, right? we want the matrix to have repeated roots, to have the same eigenvalue. So if we make the matrix upper triangular, then the diagonal is the eigenvalues. So the simplest thing we can look at. How do you,
Lower.
no, this is upper triangular.
Oh,
Upper triangular is you only have non-zero entries on the main diagonal and above. Lower triangle is you only have non-zero entries on the main diagonal and below. This is an upper triangular matrix. So how would you prove that there is no matrix that diagonalizes this?
Well, one included condition is that you can show that there is no eigenvectors at all cases.
Have we proven that yet? So if it's diagonalizable, if A is diagonalizable, there exists an S such that I think we had S inverse AS equals lambda.
We can also show that the characteristic polynomial.
So why would the characteristic polynomial work?
Then you can find the eigenvalues. And then find the
So one thing is we don't have enough eigenvectors to form the matrix S. This matrix only has one eigenvector when you try to solve it. So what that just is telling us is that we can't find a matrix S composed of eigenvectors, but maybe there's another way to find a matrix S that works. So here, maybe these aren't the diagonal entries. Maybe it's just some diagonal matrix. D1, 0, 0, D2. Can we find a matrix S? Well, let's look. If I give you the matrix 0, 1, 0, 0, take A, B, C, D. What's the inverse of A, B, C, D? D, A minus B minus C, 1 over AD minus BC. And if you check, I guess you can see it. You get AD minus BC good for the upper left coordinate, so this works. 2 by 2 inverses, yes. So this is going to be 1 over AD minus BC, D minus B minus CA. And now we've got 0, 1, 0, 0 times A, B, C, D. Oh, that's going to be lots of zeros. So for the first one, when we're going to get C, and then we're going to get D, then we're going to get 2 zeros. So then get, yes? So you get 1 over AD minus BC. And now we're going to get DC for the first one, I think. And then D squared for the second. And then we're going to get minus C squared. And then we're going to get 0. Did I make something wrong? Sorry, minus CD. Sorry, thank you. Minus CD.
C has to be 0.
So to be diagonal, we need C equals 0. And what else? So it is the 0 matrix. So S inverse AS would be the 0 matrix, or A would be S times the 0 matrix S inverse, which is just the 0 matrix again, which is false. So we at least have one matrix that's not diagonalizable. Again, you want to collect examples. With probability 1, if I write down any matrix, it can be diagonalized. But here's an example of matrix that can't be diagonalized. it's a beautiful result that any real symmetric matrix, any complex summation matrix can be diagonalized. And then we've got 2 minutes left. That should be more than enough time to prove. So theorem. A real symmetric implies A is diagonalizable. So really fast, proof. Show you can get S inverse AS equals upper triangular. Okay. What is so here S is going to be Q. So actually I want to use that there's an orthogonal matrix where I can do this. So I'm going to have Q transpose AQ. So Q is a real orthogonal matrix. I can find such a Q. So imagine I can find a Q so that Q transpose AQ is upper triangular. What kind of matrix is Q transpose AQ? If I take the transpose of that, I get Q transpose A transpose Q transpose transpose. What's A transpose? What's the transpose of the transpose of Q? So this, what kind of matrix is this? Real symmetric. But this equals an upper triangular matrix. What's the only real symmetric type of real symmetric matrix that's upper triangular? Diagonal. So if you can prove that you can bring a arbitrary real symmetric matrix into upper triangular form, it immediately improves to being diagonal if you do it through an orthogonal transformation. And what you do now is now you prove that any matrix can be brought into upper triangular form. And what you do is you do it component by component. What you do is you say AV1 equals lambda1 V1. Take V1 as the start of an orthogonal matrix and extend to orthogonal matrix. So basically, think of applying Gram-Schmidt. I've got one direction, I fill in the rest. And now I'll call this matrix Q1. And now I look at Q1 transpose A Q1. If I apply E1 to this, Q1 of E1 is V1, A of V1 is lambda1 V1, Q1 transpose brings me back. So this is going to just be lambda1 E1. I'm sorry, lambda1 V1. No, lambda1 E1. So what that means is if you look at the first column of this, the first column of this is lambda1 0 all the way to 0, and then crap for the rest. And then you just restrict yourself and you work on the smaller n-1 by n-1 part. And then for the next level, you'll just do like a 1 here. You'll put all zeros here, and then you'll do something in here. And so I'll leave you the details to just finish this up. This is one of the most important results in linear algebra, that we can put a real symmetric matrix into upper triangular form, which means it's now diagonal. And we do this through orthogonals. All right. So what we will do then and I'll send you some stuff to read, is on Tuesday when we come back from spring break, we'll start talking about properties and values of random matrices. And these turn out to model so many things in mathematics. And it'll be just absolutely amazing what we see with them. All right, so this is a good place to stop.